As we continue our quest to find digits of pi, today we will take a look at the Wallis product. This is named after the English mathematician John Wallis, who was a contemporary of Isaac Newton. This is an infinite product, meaning we multiply an infinite number of fractions together. It is similar to an infinite series, except we are not adding or subtracting terms. Computationally, the results of carrying out those operations looks like this. As always, I encourage you to make your own spreadsheet and compare your numbers to mine. Hands-on application is the best way to learn this stuff. So what's going on here? Notice the second column is pairs of even numbers. 2, 4, 4, 6, 6, 8, 8, 10, 10, and so on. Likewise, the third column is pairs of odd numbers. 3, 3, 5, 5, 7, 7, 9, 9, and so on. The number in the fourth column is a fraction. In this case, 4 over 5 is equal to 0.8. That can be seen by the red and blue boxes. The same rule applies for every other row in the table. The number boxed in purple is the product of the numbers in the blue and green boxes. Since that is equal to pi over 4, we must multiply by 4 to approximate pi. That is boxed in orange. Notice that after 15 rows, we haven't even converged on 3.1 for an estimate of pi. Extending the table to 1,000 rows, we get these numbers. Even so, 3.14 is only 2 digits past the decimal. That's not very fast convergence at all. Do you have any ideas on how to speed up the rate of convergence? Well, if I plot the first 25 terms, it looks like this. Notice that our approximations, the blue curve, oscillate above and below the true value of pi, the red line. We've seen this before with an infinite series. That time, we took the average of adjacent values to get a better estimate for pi. It is tempting to do the same thing here, but if you try, and I encourage you to explore this on your own, the numbers won't work out very well. Now time for some technical details. When I said average, most of you were probably thinking of what mathematicians call the arithmetic mean. Given two numbers, add them up and divide by 2. Visually, that can be thought of as a mass balance. In this case, 4 plus 10, all divided by 2, is equal to 7. So that's where the scale balances if we position a fulcrum there. Of course, the arithmetic mean can be extended to any number of input values n. In a previous lesson, applying the arithmetic mean helped us speed up the rate of convergence of an infinite series. But this time we are looking at an infinite product. When I applied the geometric mean, I got much better results. What is the geometric mean? The geometric mean is defined like so. Given two numbers, multiply them together and take the square root. This can also be generalized to any number of input values n. While I cannot give you a rigorous reason why this works out, there are some interesting patterns to note. Infinite series, adding terms. Arithmetic mean, adding numbers. With an infinite product, we multiply terms. The geometric mean has us multiply numbers. So what is the geometric mean? This topic is often neglected in school curriculum, so I will give a brief overview here. The following is a visual demonstration. Look at this right triangle. Now we are going to split it with the red line such that two smaller right triangles are formed. These are similar triangles. We can use ratios to say that A over H is equal to H over B. Small leg over big leg on one triangle is proportional to small leg over big leg on the other triangle. Using that proportion, we cross multiply. A times B is equal to H squared. Take the square root of both sides. H is equal to the square root of A times B. That is the geometric mean. Visually, h is longer than a and shorter than b. It falls somewhere between those values, but not halfway, as in the case of the arithmetic mean. Alright, so let's apply the geometric mean to our table of numbers. That is seen in the last column on this screen. Notice that after 15 rows, we have converged to 3.14, 2 digits past the decimal, already much better than before. To get this, multiply the two numbers boxed in green, then take the square root. That gives us the number boxed in blue. The same rule applies to every other row in the table. Make your own spreadsheet and verify this for yourself. Graphically, plotting the last column looks like this. The oscillations are much smaller than they were before. The blue curve hugs the red line much more closely. If we take the geometric mean a second time, we get even better results, 3 digits past the decimal by the 15th row. The oscillations on the graph would be even smaller. As we did with the infinite series, we can keep taking the mean. This adds a new column each time. Here I have gone to the 100th term and applied the geometric mean 8 times. Notice the triangular shape on the right. I can save some computational effort by not taking the geometric mean of all 100 rows. These numbers are probably too small to see clearly on the screen, so let's zoom in a bit. Here is just the triangular region. For each new column, we take the geometric mean of the two numbers in the column immediately to the left. Observe that we gain about 2 digits of accuracy each time we take the geometric mean, at least for the 100th row of this table. By the last column, we have maxed out the number of digits this software can handle. That was an overview of how we can implement the Wallis product to compute digits of pi. In the next lesson, we will focus on how to derive the Wallis product. It should not be surprising that this also falls back on trigonometric foundations. Thanks for watching. I look forward to seeing you again.